Hi, my name is Peyton Ecklund. I'm a first-year master's student at the University of Florida in the program of Horticultural Sciences. My advisors are Dr. Xiaoying Li and Dr. Shoan Shang, and we're based at the UF Tropical Research and Education Center.
The first goal of my project, funded by the USDA, focused on evaluating okra germplasm for seed-borne pathogens. Seed-borne pathogens are disease-causing microbes that adhere to the seed surface or below the seed coating and use them as a means of survival and transmission. These pathogens can cause germination reductions and diseases like damping off, root rot, wilting, and leaf spots, which reduce crop yield. The issue is that these pathogens are not visible to the naked eye, so contaminated seeds can easily spread pathogens to different farms or even countries. Additionally, once introduced to an area, they often produce long-term survival structures, so the pathogens can remain in soil for over a decade, causing yield losses season after season. Many seed-borne pathogens are limited to infect one or a few specific hosts, but others, like a fungus I work with, have extremely wide host ranges. While screening okra seeds, I isolated many pathogens, including Macrophyllina fasciolina, a fungus believed to cause rots and damping off on 500 plant species from over 100 families. This is an important discovery because Macrophyllina can cause significant damages to Florida's major crops, including strawberries, peppers, legumes, and cucurbits, particularly watermelon. The management of seed-borne pathogens can be difficult because they are hard to detect and often require chemical fungicides to eradicate. However, chemical fungicides are toxic to the environment, and due to Florida's high water table, the risk of contamination is high. This has made the need for sustainable practices, like rapid seed screening, more urgent. Traditionally, seed-borne pathogens have been detected through blotter tests, but these assays are time-consuming and unsuitable for large-scale seed screening. To address this, another objective of my research is to develop a sensitive and specific molecular diagnostic using polymerase chain reaction, or PCR. PCR allows us to screen large batches of seeds and detect the presence of specific pathogens by targeting a unique region of their DNA, like a fingerprint. This way, plant pathologists can process okra seeds for Macrophyllina DNA, for example, and know within a day if the seeds were carrying the pathogen. By optimizing early detection methods such as seed screening, we can prevent contaminated seeds from entering fields and causing yield losses. This is essential to preventing the spread of plant diseases and ensuring the long-term stability of local crop production. But if a seed-borne pathogen is already in your field, a good strategy for managing the population is by growing crops that are resistant to that pathogen. So, the final goal of my project is to determine the resistance of common okra varieties. Resistance can be defined as incompatibility, where a pathogen is unable to cause disease on a certain plant species or variety. By defining the resistance of okra varieties against these problematic seed-borne pathogens, crop productivity can be protected, and Florida growers can maintain healthy fields.